everybody. So last time we looked at the p-type inequalities. We end up with the knowledge that some function has bounded R variations. And today we want to come back somehow to the first talk. So we want to consider ergodic averages. Here I will stick my attention to trajectories over squares. And I would like to give you a proof. It won't be probably complete proof, but almost complete proof of R variational estimates for these averages, and this is for R greater than 2, and I will stick to L2. Okay, there is a quite nice argument which is based on the fact that the averages are non-negative, which allows to consider only lacunary sequences to prove pointwise convergence. In fact, it's not sufficient to consider just 2 to the power n, but it suffices to consider, let's say, tau to the power n where tau is very small. It's close to 1. Okay, but the proof is exactly the same. We just change 2 into a tau and it works. Okay, so this is just a technical thing, and using the Calderon transference principle, we can reduce our task to showing this variational estimate for a very particular system, that is integer shift system, in which averages are of this type. Okay, so during the first talk, I gave you this reduction for maximal operators, but it works also for variational estimates, oscillatory estimates, and for jumps. All right, so please remember that our averaging operator is just shift by consecutive squares. All right, so some notation, which I suppose it's standard. So we have tobus, we identify 0 with 1, then we have fractional part of a real number, then we have complex character function, then the Fourier transform, I write Fourier transform with plus, but it does not matter. Then the discrete Fourier transform, we will use Plancherel theorem, and the corresponding inverse Fourier transforms are given by F inverse with a subscript R or with subscript Z. Mainly I will use this identities, well, these objects for d equal to 1, because we are in one-dimensional situation. All right, so let us start. So the first thing is how this situation looked like in the continuous setup, and I would like to convince you that in fact this question in a continuous setup is straightforward in the sense that it follows from the classical bounds for the cardinal to maximal function. So the continuous counterpart is similar as in the discrete. The difference is that instead of having sum, we have an integral. And what happens here is that we can use the change of variables trick. So we can introduce a new variable z, which is y squared. And then our averages looks like here. And in fact, what we can do is we can dominate this maximal function by the Hardy-Littlewood maximal operator. And how to do that? So the first thing might be that we see that this average is in fact a convolution with L1 dilation of this function. Okay, so what I did here is I extended this original integral into a symmetric integral, and this is our basic function, and we consider L1 dilations as before. And we have this quite general result, which tells us that if we consider the maximal function based on convolutions with L1 dilations of a function which is non-negative, let's say, okay, we do not assume integral 1 because we put one more here, but what is very important is that this function is radial. It's radial and it decreases with the radius. Okay, so in other words, this function phi can be written as a function on a real line, in fact, on the half of the space. And it depends on the radius, and this new function g is decreasing. Okay, so this is a very important assumption, and then this maximal function based on these convolutions is dominated by some constant times the harmonic maximal operator. All right, you have any questions? So here, what happens is that this continuous counterpart can be, it is a convolution with L1 dilation, so it can be dominated by the harmonic maximal operator. So at least for the maximal function for this continuous counterpart, LP boundedness and in type 1 is very easy. Here I have a proof of this lemma, but I think I will omit it. But this is a very nice proof, which I think usually does not appear in the literature. I learned this argument from Carlos Perez some time ago in this building, well, in the math department. So if you are interested, then please look at the slides, which I send you. But let us now focus on the discrete setup. So the main difficulty in our discrete setup is that there is no change of variable technique. So we cannot directly reduce our situation to, let's say, discrete harmonic to maximal operator. Okay, and the second problem is that, as we will see in a moment, in a continuous situation, we have a very nice decay of the continuous Fourier transform of our continuous averages when the frequency psi is non-zero and it does not appear in the discrete situation. So in a moment we will see this effect. So first, let us compute the Fourier transform of those continuous averages. So here you have a definition. So we just compute we use the definition of the Fourier transform, and then we shift the integration in x by this y squared. So we obtain an additional character with y squared. Here in the middle, what we get is the Fourier transform of f, and the remaining part is our symbol. So after changing the variable such that instead of having an integral over 0n, we want to have an integral over 0,1, we get this symbol. Okay, so this is a symbol related to continuous counterpart of our problem. So this is this symbol I will denote by phi with subscript n. And now let us look at the decay of this symbol at 0 and at infinity. So at 0, when we compute this symbol, it is just an integral of 1, so it is equal to 1. So if we are interested in the decay, at 0, we need to compare with 1, which is a value at 0. Okay, and what happens then is we just use the definition. So then we put the absolute value inside the integral, and then we use the fact that the character -1 is dominated by what we have in the power here. So we get this estimate because t is just from 0 to 1. Okay, so t is bounded. Okay, do you have any questions concerning this part? All right, so we have a nice decay at 0, and in fact, in a continuous setup, we can have something like that as well. But the problem is with the decay at infinity. Okay, so here is a definition of this symbol. So it is an integral from 0 to 1. Then we have character, n squared t squared times psi. All right, and to have a decay at infinity, we can use the classical van der Korput lemma, which tells us that if so derivative of the frequency is bounded from below by some number, then we have a decay with respect to this number. This is more or less what van der Korput lemma tells us. This lemma works also for k equal to 1, but then we additionally need to assume that the derivative is a monotonic function. But here we will use van der Korput lemma with k equal to 2, because when we compute the derivative of the phase function, well, if we compute the second derivative, then t disappears, and we have just n squared psi. Okay, so in that way, we have a decay with respect to this quantity. Okay, and we have this power -1/2 because k is equal to 2. But in fact, in our method, it does not matter what is exactly the quantity of what is the size of this power. For us, it will be sufficient to know that this is some negative power of this expression n squared. All right, and here is an observation that once we would know that we have a sequence of multiplier operators with corresponding symbols t and psi with this decay. So it has both the decay at 0 and the decay at infinity. Here, this is not our case in the sense that we do not have this second decay because the multiplier is equal to 1. We have it once we subtract 1. Okay, but let's assume that our situation would be even easier. Then using Planck-Schorel theorem, we can easily conclude that the maximal function is L2 bounded. And this is quite easy because we can dominate this maximal function by a square function, use the Planck-Schorel, and what happens with the symbol is that we will end up with such sum. Okay, and this sum is just two-sided geometric series, and one can easily compute that the result is bounded uniformly with respect to sum. All right, so so this is the way how to deal with the maximal operators based on symbols which satisfies this which possess this decay both at infinity and both at 0. Well, I forgot to mention, but here we by decay we mean that if we fix n, then that if we fix psi, non-zero psi, then we have a decay with respect to n. Okay, and this will be the case in the discrete setup, as we will see in a moment. All right, so let us look at the discrete situation. So we have our averaging operators. So we average from 1 to n. The function f evaluated at x minus n squared. And then we compute the Fourier transform. So in the first line, we just use the definition of the Fourier transform. Then we use exactly the same trick as in the continuous setup. That is, we shift the summation in x by n squared. So what we get is the Fourier transform at point a divided by q. Sorry, I forgot to mention that first of all, we want to compute this discrete Fourier transform only at points which are fractions. Okay, and we assume that a and q are co-primes because it's much easier to compute Fourier transform for those points. Okay, so then what happens is we have a Fourier transform at this point times this average. Okay, so this comes from the fact that if we shift by n squared, then we will get additional character, which is n squared a over q. Okay, so we end up with this symbol. And now let us analyze this symbol. So this is exactly that symbol, And what we see at the very beginning is that the function which appears here as a function of n is q-periodic. So it's quite natural to split this summation n into classes modulo q. Right? So we introduce a new variable, qn plus n plus r, and then we split our summation into two sums. Okay? So the sum in R is a sum with respect to what we get if we divide n by q, and we have the remaining sum. We do not care if n is divisible by q or not, because we do everything up to an error term which is of this order, q over n. Okay. So then if we apply this, when we decompose our original summation in n into these two pieces, then we can easily observe that this expression here does not depend on n. Okay, because character is one periodic and this function is therefore a q-periodic. All right, so we end up only with this short sum up to this error term. So here we think that q is fixed, it's much smaller than n, and we tend with n to infinity. So this expression does not depend on n at all, and here this converges to 0. Okay, so for a frequency which is a over q, we see that if n tends to infinity, then the corresponding multiplier tends to some number, and thus we will see it's very rarely 0. Okay, because if we take, for instance, a over q equal to 1/3, then using the above approximation, we can see that this very low sum, very low sum of some sort of random numbers, which are of modulus 1, reduces to a very short sum, which has only 3 terms, and which can be easily computed, and this is the result, right? And this number is just non-zero. Okay, so what happens here is that if we take a frequency which is non-zero, it may happen that it does not decay to 0 when we take n larger and larger. Okay, and this is a problem in discrete analysis, because somehow in the continuous setup we may think that 0, the frequency c equal to 0, is some sort of singularity, and here in the discrete setup, all fractional numbers with small denominators can be seen as some sort of singular points. All right. So let us introduce the average which we already had on the previous slide. Right. This is the average we want to introduce here. So this is called a Gaussian sum. I think that traditionally it is defined only for irreducible fractions, a over q, but formally you can define this for any fraction, a over q, and the resulting right-hand side does not depend on the representation of this fraction, because everything is q-periodic. So for instance, if you represent 1/3 as 2/6, then formally you have larger sum, but because of periodicity, it will reduce to a smaller sum, right? But it's quite convenient that to think that a over q is irreducible fraction. All right, it's clear that this expression as an average of numbers which has modulus equal to 1 is dominated by 1. But in fact, we will be able to get a much better estimate. So we'll be able to have some decay with respect to the dominator of this fraction. And that's why it's quite convenient to think that this definition is only for irreducible fractions, because otherwise we would be able to do stupid things like artificially increase our dominator and think that we have as good bound as we wish, right? So from the beginning, it's just convenient to think that this definition is only for irreducible fractions. Well, yet another remark is that here the summation in R is from 1 to Q, but because of the fact that this function as a function of R is Q periodic, it suffices to take any other set, which is a set of complete residues modulo Q. Okay, so in particular, we may change this Q into 0 because it gives us the same rest after dividing by Q, or what we will do in a moment, we can replace this set 1 Q by any other set of consecutive numbers of length Q. All right, and this estimate, which I already announced, can be easily deduced from Weil's inequality, which I will state later on, and this is how it should be done. But here we can do it also by hand. So I will prefer to do it by hand and show you how it can be easily deduced. And we will use the so-called differencing method. So we will start from an expression that in the phase here, as a function of R, we have a quadratic expression, and we want to reduce it to a linear expression. Because, well, the trivial observation is that if we will have here just R, then we can easily compute this expression, because this is just a geometric sequence. All right, so let us prove. So what we want to do is we want to bound this Gaussian sum by 1 over the square root of Q. So for technical reasons, to do not repeat Q on the right-hand side, we multiply G by Q. So we have just a sum on the right-hand side. And what we do is we consider square and write down the square as G times G bar. Okay, so R2 comes from G and R1 comes from the G bar. Okay, so this is just a definition of G. I did nothing in the first identity. And then what I want to do is I want to change the summation in R2. So instead of summing from 1 to Q, I want to sum from R1 plus 1 to R1 plus Q. So that's why instead of R2, we have R1 plus R, and we sum over R's, which are from 1 to Q. Okay, so we use this fact that it does not matter what is the set of summation. What matters is that it gives us all rests, well, the complete set of residues modulo Q. So once we have this identity, everything is much simpler, because what we have here is that if we write down this square, then we cancel out R1 squared, and we end up with this expression, which as a function of R1 is just linear. So we can use now the fact that characters are orthogonal, or we can just compute this sum here, because this is a geometric sequence. So there are two cases. The first one, let's say, is that this expression here is an integer, so Q divides B. So then we sum once, and we have Q once. So then we have Q. And in the other situation, if we compute directly this sum, then we get 0. Okay. And if we plug in this information into this expression for the square of G, then what we get is that we still keep the summation in R, and the summation in R1 gives us this expression. So this gives us this Q times this characteristic function. And now we use the fact that A and Q are coprimes. So in fact, this restriction here is that Q divides 2R, okay? Because A and Q are coprime. All right, so we have this expression, but with this constraint instead of that one. And what might happen here is that at most we can have two non-zero terms in this very large sum. The first one might occur when R is equal to Q over 2, in the case when Q is even. And the second one appears when R is equal to Q, right? Then Q divides to Q. Okay, so this means that this large sum has at most two elements, so we can bound this by 2. All right, and then we get our estimate because we divide by Q squared, and then we take the square root of the left-hand side, and we have 1 over 2 the power 1, right? All right, so here what we have is that well, this expression is more or less what comes when we compute the Fourier transform of our discrete averaging operators at frequency A over Q. So we expect that if the fractions are with large denominators, then we have some decay with respect to these denominators. So that's somehow motivates our next splitting into major and minor arcs. So here we want to use the circle method established by Hardy and Littlewood when they wanted to compute, well, they wanted to solve Warring problem in the sense that they wanted to compute the asymptotic expression for the number of lattice points on Euclidean spheres. So they were interested in computing the number of solutions in integers of the equations of type x1 squared plus x2 squared and so on up to xd squared equal to n. Okay, and then they use this very nice technique. So here what we want to do is we introduce a function eta, which is a bump function, and which looks like that at the neighborhood of 0, this function is equal to 1, and then it decays to 0 on the twice larger neighborhood, let's say. In fact, if we consider just a two-boundedness, here instead of taking smooth function, we can just take indicator function. All right, and what we do is that we have an interval 0, 1, and we take only fractions with small denominators. So this means that the denominators are smaller than A. So we take denominators which are smaller than very small power of n. And then at each fraction with such small denominator, we take an interval of length approximately 1 over n squared. Because of technical reason, we need to put this epsilon here as well. This comes from the fact that when dealing with this remaining part, we will need to have this interval to be a bit larger. They are called arcs because we may think that the torus is just a circle, and then if we take the neighborhoods of those fractions with small denominators, then these are just arcs. Okay, and they are arcs of length 1 over n squared. Well, times n to the epsilon, but we may think that this epsilon is 0 informal. All right, and this is in some sense quite natural because if we consider fractions with denominators which are larger than this n to the power epsilon, then we have a very nice decay of this Gaussian sum, right? Because it has a decay of type q to some negative power. So here we would have a decay of type n to some minus like that. All right, and here the remark is that if we look at at the supports of these eta functions, then if we take two different fractions, then the supports are different. So in fact, these are very small arcs around those fractions, and those arcs are different. All right, and the first expression will be the part related to major arcs, and the second one will be related to minor arcs, and we denote similarly the corresponding operators which are behind these symbols. What is worth to mention here is that the behavior of these two symbols is completely different. So the part which corresponds to minor arcs, from my point of view, it's more mysterious. But on the other hand, it has this nice property, which we'll see in a moment, that it has a decay with respect to n. So it might be considered as an error. But on the other hand, this part related to major arcs, it will not have a decay with respect to n, which we already seen, because in particular, in this part, we will have frequencies which are equal to A over Q. So then what we get is that this multiplier is just equal to the Gaussian function. But on the other hand, this part related to major arcs can be easily approximated by objects which we can analyze. Okay, so the behavior of these two parts is completely different. And first, we want to focus on minor arcs, but before we do that, let me show you the following lemma, which tells us that every real number alpha can be approximated by some fraction in a diaphantic way, in the sense that if we take large Q, then we can find a fraction with denominator at most equal to this Q, such that the approximation is of this type. So in particular, it's smaller than 1 over a large Q. So this large Q tells us how good is an approximation we want to have. But on the other hand, if we take very large capital Q, then the denominators might be very large, right? So we need to somehow, later on, we need to optimize how large Q we want to take. Well, yeah, so let us look at the proof. So we may think that, well, actually, we may think that capital Q is just an integer. In general, we can take any real number. And then we decompose an interval 0, 1 into n plus 1 intervals, each of them of length 1 over n plus 1. And since we have in our disposal n potential denominators and n plus 1 choices, then what we do is we first look at the situation when one of the fractional parts of those denominators belongs to the most left interval. Okay? So then if we look at that, then taking a equal to the floor function of q times alpha, we can easily see that q alpha minus a, which is by the definition fractional part, and since we know that this belongs to this interval, we know that this is at most 1 over n plus 1. And we have our approximation. Okay. Then the second case is quite similar. So here it's symmetric, and we assume that the fractional part belongs to the last interval, so the one related to capital N. And then if we consider these two cases, then the last case is that all fractional parts q times alpha belongs to one of the remaining n minus 1 intervals. So then it means that there are two q's such that its fractional part belongs to the same interval. And then we can proceed in a quite similar way in the sense that we have this q1 alpha and q2 alpha, which belongs to the same interval of length 1 over n plus 1, and then we can define mu q, which is a difference, so it is between 1 and n, and as a, we can take the difference of the corresponding sub-functions of these expressions. And if we compute this difference, then we end up with the difference of fractional parts, and since they belong to the same interval of length 1 over n plus 1, then we have this estimate at the end. Okay, so the proof is just an application of pigeonhole principle that after analyzing these first two cases, we have a situation that we have n-1 intervals and numbers. So there are two numbers which belongs to the same interval. All right, but well, maybe the proof is not so important. The thing is that this approximation is almost optimal in the sense that if we would require that our approximation is twice better, and then in fact this fraction is unique. All right, and the second thing is that from this approximation, since q is smaller than capital Q, one can easily see that this expression here is smaller than 1 over q squared. Okay, and this kind of approximation is called Diophantine approximation. So every real number, okay, so this lemma shows us that every real number has a Diophantine approximation. All right, and we will use this lemma to deal with the part of our operator which is related to minor arms. All right, so here we will use variance inequality, but before we do this, let us give the following simple observation that if we would be able to show that our symbol has a decay with respect to n, which is that we say a power of n, so we have a decay of type n to the power minus alpha, and alpha is might be arbitrarily small, then this means that this is the end of our job, because what we can do is we can estimate R variations by 1 variations, and yesterday, 2 days ago, we have seen that R variations can be dominated by just small L R1 of the corresponding sequence. So we do not assume that, well, we do not take into account any cancellations. This is a very important estimate. And so once we do that, we just sum over n each L2 norm of the corresponding operators. And since symbol has this decay, it means that this operator has the same decay. So in fact, the point is that if we consider the dyadic space, everything is small. So we can end up with just normal operator. Okay, so our aim now is to prove that the part of our symbol related to minor arcs has this power okay, with respect to n. Another observation is that in fact we can treat in the same way any other part which has this decay. So in some sense we may think that this part is a kind of error. Okay, so once we will know that the error terms has this power decay with respect to n, then we do not need to consider the property of variational estimates. All right, so to prove this decay for the minor arcs, we need to introduce variance inequality. So our situation is that we have this exponential sum. So in the face, we have a polynomial of degree n with coefficients which are psi1, psi2, and so on up to psi d. In our situation, the symbol, sorry, I do not have the definition of the symbol, but this was just an exponential sum with psi times n squared. So in our situation, this face will be degenerated, in the sense that we will have just one term, psi times n squared. But Weis inequality works in such generality that we have n polynomial here, and the coefficients are corresponding psi. And if we know that some of the coefficients, so let's say psi j, has a Diophantine approximation by fraction a over q, which is irreducible, then we can estimate this exponential sum by the following expression. So we have additional logarithm. Okay, so the first trivial bound is by 1, right? Because it's an average, and we want to gain some. So here we have additional logarithm, but we expect that we will have a decay from this kappa function, well, kappa parameter, and kappa is the minimal value of q and n to the power j divided by q, because we assume that the j frequency is approximated, so the scale related to psi j would be n to the power j, so that's why n to the power j appears here. So in order to have a decay, it's optimal to choose q, which is large enough, but not too large. So the choice when q is between some power of b and n to the power j minus this power is in some sense optimal, because then we can see that this kappa is from, well, this q is larger than n beta, and this expression is also larger by n to the power beta. Okay, so at the end, this kappa is of size n to some positive power of n. So here we would gain some power of n, and this logarithm does not matter because we can eat this by this power of. Okay. You see that? Okay. So we will use Weis inequality to deal with minor arcs. So what happens here is that we, in our situation, the corresponding symbol is indeed an exponential sum where we have only one non-zero coefficient. So the first thing is that we want to use Dirichlet principle to approximate our coefficient, which is psi. So we can do that, and as a capital Q, we choose this expression because we do not want to have Q which is too large. So this is the power which we have here that we consider squares, and we want to take a power which is a bit smaller. Okay, so by Dirichlet principle it's possible, so we can find such fraction. And then we have two cases. So the first one is that Q is relatively small, so then we do not expect any decay from the Weis inequality. But on the other hand, then the fraction A over Q belongs to this set, because this is the set with denominators which are smaller than n to the power epsilon. So here we have the square root of this expression, and thanks to this estimate, so in particular this is smaller than just this part only with n. It means that the corresponding projection is equal to 1. So at the end, this 1 minus this projection is equal to 0. So our symbol is just equal to 0. Okay. On the other hand, if we assume that Q is large, then we can use directly Weis inequality, because we have this situation that Q is large, but not too large. So this kappa, which appears in Weis inequality, is at least equal to n to some power. So here, what we get in this estimate is that from this expression we save some power of n, and we can easily this logarithmic function. So when we want to compute this explicitly, then this exact power appears here, and what we get is is yet a bit smaller power, and we have the estimate we wanted to have, and we can conclude the proof of this part of our operator. All right, and now we want to deal with major arcs. So here the situation is completely different in the sense that we do not expect any decay of the multiplier. But on the other hand, since we are in major arcs, we are very close to fractions, then we expect that we can somehow approximate our original symbol by the symbol which corresponds to these fractions. All right, so here we will approximate our symbol. So so here is the part which is related to major arcs. So we have our original operator, original symbol, and then we consider only xi's, which are very close to fractions with small denominators. So this is exactly the situation of this lemma. So we have fraction with small denominator, and we have exactly the same scaling as in our functions eta. And we want to approximate up to admissible error term our symbol f. And here we can more or less proceed as when we considered our symbol for fraction a over q. This is what we did at the very beginning, that we observed that if we computed the Fourier transform of our averaging operators, then we just got Gaussian sums. So we obtained this one, and so this agrees with this expression, because when we put psi equal to a over q, then we have our continuous symbol at point 0, which is 1. Okay? So we get just a Gaussian sum. All right, so we proceed exactly in the way we did before. So we split into classes modulo q. So when we split our original character, so n squared times psi into these two pieces, then we see that this piece is q periodic. So if we write down that n is equal to qn plus r, then what survived in the first one is just r squared. So this is exactly our Gaussian sum, but the problem is that r appears only in this expression. And here we cannot do nothing. We just know that this expression is very small because of our assumption that we are in a very small neighborhood of the fraction a over q. All right, so I do not want to analyze this in detail, but what happens here is that this is what we got on the previous slide. The only difference is that I split this 1 over n into 1 over q here to get Gaussian sums, and the remaining part, which is with scaling q over n. And then, thanks to the fact that that psi is very close to a over q, in fact, this expression here can be approximated by the corresponding integral. And this corresponding integral corresponds to our continuous symbol at the point alpha, and alpha is a difference between psi and a over q. Let me not give you the details. The important thing is that we may think that our discrete symbol is in some sense a weighted average of continuous symbols. The weights comes from Gaussian sums. And here we just use this translation in the sense that if we are with psi close to the fraction a over q, then it's the same as thinking that the continuous multiplier is closer and closer to 0. So that's the somehow that's what I meant when I said that in the discrete situation we do not have some sort of singularity only at zero, but we have a singularity at every point with small denominator. Okay, and this is the interpretation comes from the fact that we have this continuous symbol. All right, so now what we do is we want to deal with the major arcs. So what? All right, so the definition of the symbol related to major arcs is given here, and we know that we can, up to some admissible error term, we can replace this symbol because we are in the range where our frequency is close to fraction. We can replace it by this Gaussian sum times continuous multiplier. So more or less, we can replace our original symbol by this expression, except that here we sum over all fractions with denominators which are at most n to the power epsilon. But now what we want to do is we want to split this sum into fractions with somehow fixed size of the denominator. So we do it diagonally. So in fact, the way we do it is such that the corresponding denominator is of size 2 to the power s. And the reason why we do that is that we already know that this Gaussian sum has a bound which is q to some negative power, which is in our case 1/2, but in fact this 1/2 does not play any role. It suffices that we know that there is some power saving of this Gaussian sums. So what we can do is we can write down our symbol related to major arcs as a sum of these symbols, which are the approximation which comes from the previous lemma. And here we choose, well, we take denominators, we collect denominators with the same size of, well, we collect fractions with the same size of the denominators. And again, using triangle inequality, we can move the summation in S in front of the norm. And this error term is admissible in the same way as we see it works for minor arcs. So we can just sum the corresponding bounds for the norms and the corresponding symbols. All right, so now what suffices to do is to prove that these new operators have R variations which have exponential decay with respect to S, so with respect to the size of the denominators. And we expect that we will have some decay with respect to S, which is of exponential, some exponential decay with respect to S, because we already know that Gaussian sums has a decay with respect to Q, and Q is of size 2 to the power S. So in fact, for 3 we have the decay 2 to the power S over 2. All right, so here we, when dealing with such single scale S, we want to have this exponential decay with respect to S. And what is convenient to do is to split this further into small and large scales. I will not have time to cover large scales, but in the case of large scales, what one do is we try to transfer the analogous result from continuous counterpart. Okay, and here I would like to deal with, well, actually, I will not have time to deal with small scales as well, but I will briefly tell you how to do that. All right. So what we do is we have this variation semi-norm. Equivalently, we think that here we have a maximal operator, and the scale is that capital N is greater than S over epsilon. So we make additional cutoff at the level of kappa S, and kappa S is chosen in the way that the logarithm of this kappa is much smaller than the exponential function. But on the other hand, if we take the lowest common multiplicity of all denominators from our set R to S, that is denominators which are at most 2 to the power S plus 1. So if we take at most this number, so 2 to the power S factorial, then it turns out that if N is greater than kappa S, then this number is still much smaller than the exponential of our scales. Okay, and this is crucial in the argument to show that large scales can be compared to the continuous version of our problem. All right, so for small scales, in order to reduce our variational estimate to a square function, and later on we may think that this part is it's in fact some sort of singular integral. We use the following Rademacher-Menshoff inequality. Well, this version here is much nicer to see and to analyze. So what happens here is that, let's say that we have two variational semi-norm on the left-hand side, and we can dominate it by some sort of square functions. So here, it's convenient to think that I is fixed, and then what happens here is that we have some sort of square functions. So we take the differences of the consecutive dyadic numbers from scale I. Okay, so this looks like a square function. And in our application, N will be very small with respect to S. So in fact, we can separately consider each square function. Right, and well, this will be my last slide. So in fact, this Rademacher-Menshoff inequality is very useful if we want to. Sorry, this is a proof, so I will omit this. But this is a very nice tool which allows to reprove the original result of Rademacher and Menshoff from 20s of the previous century, which says that if we have okay, so we have orthogonal basis phi n, and we consider partial sums. Then the original result of Rademacher and Menshoff was that if we compute the maximal operator restricted to the scale n, then in a such generality, we cannot prove maximal estimate with uniform bound, but we have this logarithm here. So this was a very this is still a very nice result, which tells us that in generality, if this is sharp and it turned out to be sharp, that we cannot get rid of this logarithm, we cannot expect that partial sums will converge pointwise, let's say, if we consider, let's say, orthonormal basis on the interval 0, 1 to the original function. But on the other hand, in the famous paper of Carleson, he was able to improve this inequality in case of the standard base on L2 on the interval 0, 1. All right, so I think this is a good moment to stop. So sorry to do not show you the whole proof of L2 boundedness of the corresponding R variations in a discrete setup, but there is no chance to do it at 5 minutes. So thank you.
Thank you very much. Any questions?
You mentioned several times that precise estimate for Gaussian sums is not relevant here.
Yeah. Yes, but okay, so we have here this estimate, right? And this is in fact sharp, yeah. So by that I mean that this power is not relevant.
Yeah. So my question is, there is some application in this theory of sharpness of this Gaussian powers.
I think there are, yes. I think that they are used also in this Gaussian problem with the circle and. Well, I do not know exactly, but I think it's relevant in that problem. That
You can't circle problem.
Yeah, I think that it's used there. But I do not know. It's okay.
What is the advantage of taking these smoothing factors?
For L2, there is no advantage of taking that. But if you want to have LP theory, then it will not. And in fact, LP theory is much more complicated in the sense that you need to use some more advanced things, like for instance, UNESCO Wenger projections and so on. And it is very relevant that instead of taking indicator functions, you have smooth functions.
And could you repeat once again why is it sufficient to consider these variational estimates for lacunary sequences?
Okay, yeah. So I omitted this argument, but yeah. So it was yeah. So in fact here is a precise proof, but I do not want to. Let me do not show you. I can just tell you that. And more or less, if you assume that, okay, if you consider this dyadic space, then from, in particular, you know that the variational semi-norm is finite, so you know that there is a convergence along the dyadic scales. Okay, and then you can, instead of taking just the scales 2 to the power n, you can take scales which are 2 to the power n divided by s. And let's say that s is a very large number, but fixed. Okay, so if you consider variations along such dyadic scales, then for each s you have a limit. Okay, and since the dyadic scales are a subset of those dyadic scales which are of the form 2 to the power n divided by s, because in particular you can take n equal to s times integer. Okay, so then you can show that along each such lacunary sequence, you have the same limit. And having this knowledge, working a bit, you can show that in fact you are able to have convergence along all integers. We can talk about that after.
You don't need to know that the estimate is. You don't need to know the dependence on S. No.
No, so it suffices to prove variational estimates for instead of 2 for tau to the power n. Tau is very small in the sense it's close to 1, and the corresponding constants here might depend on n. So you do not need to have the uniform bounds. In fact, it's well at the end. That's true.
Is true, right?
Yeah, because at the end it's possible to get R variations for integers. In particular, if you take a subsequence, then you have smaller expression.
Any other questions? Okay, if not, let's thank Tomek again. We now go.